Yeah, good afternoon, everyone. Very warm welcome to our ETH webinar, AI for Spatial and Transport Planning. My name is Andreas Rupf. I'm head of ETH Raum, which is a platform for a wide range of services in spatial development, but also education. So we link practice with research at ETH Zürich, and I have the pleasure of hosting this 1-hour session today. So we are happy that we have practitioners joining us from many different countries and time zones. So it's great to have such an international audience with us. Before we dive in, I would like to ask you for a small interaction. So please say a quick hello in the chat and let us know from where you are joining today. This gives us a feeling for the diversity and background in the virtual room. So please use the chat tool so that we can see where you're from. So people from Germany, Switzerland, of course, but I think also from international backgrounds are with us today. So looks great, cool. Over the next hour, we will look at how AI technologies can support better, safer, but also more sustainable mobility and planning decisions. AI allows us to work with complex data, issues, simulate different futures, and understand how various models of transport interact in the real urban systems. So I'm very pleased to welcome our two speakers. One is Lucas Ballo. He's the co-founder of GoNeon, a future ETH spin-off soon, I guess. And Lucas Ambühl, also co-founder of Transcality, an already ETH spin-off. So I'm really proud to have them with us today. So let me briefly outline how we will use our time. So we have each speaker will give a compact input focusing on specific aspects of AI in spatial and transport planning. So they will have 20 minutes. And finally, we will open the floor for your questions. So please feel free to post questions in the chat at any time. You can also upvote questions that are particularly relevant to you. So I will pick up as many of them as possible in the last part of the webinar where we have the Q&A. Yes, with that said, let's begin. Lucas, I would like to hand over to you for the first input, and please introduce yourself briefly.
Hello, everyone. My name is Lucas Ballo. I am the co-founder of GoNeon. I recently finished my PhD at the Institute for Transport Planning at ETH, focusing on street networks and infrastructure design and how we can envision larger changes in our built environment. And during my research, it became clear to me that we urgently need innovations in this space, and that's the reason why our team is now turning this research into practice. My colleague, Lucas Ambühl, also studied at the same institute some longer time ago, and will also briefly introduce himself.
Thank you very much, Lucas. As Lucas, it's always fun to be in a call with so many Lucases. Has introduced, we're from the same family, let's say. I also studied at ETH Zürich in the Institute for Transportation. Did a bit more in the modeling field, and I'm happy to be talking about how to look into impact on traffic today. Thank you very much for having us.
Great. And today we will, in the next 40 minutes, we will talk about how these two different approaches that we are pursuing in these two different teams, how they work together to revolutionize the way we plan the future of infrastructure. First, GoNeon. We focus on infrastructure planning with AI agents that enables much faster design cycles and a much wider range of possibilities. We all want livable streets, right? But to actually achieve this, it is really complex. Our built environment faces a lot of different demands. Aging population, climate change, and population growth, they all create a lot of demands on the existing built environments. While the streets cannot be increased, while the streets cannot grow easily, there is more and more demands that need to be satisfied within the existing infrastructure. And this is not only in Switzerland, this is a wider issue also in many other growing economic centers. Rapid population growth puts infrastructure under strain, and we need to get more and more out of the same public space. Now, when we look at this example of an intersection in Zurich, there are clearly a lot of conflicts that need to be resolved on the ground and in the allocation of public space, so that the public spaces not only work for the pedestrians and for the traffic, but also for the businesses and all for the different demands that we pose on these public spaces. But it gets even more complex once we look at the infrastructure underground and all the engineering utilities associated with it. These make it incredibly complicated to make any changes in the existing built environment. And as a result, our planning projects often become multi-year exercises of countless discussions and dozens of specialists involved and dozens of design variants that need to be created in months and months of lengthy design cycles. And this leads to a lot of cost, very slow progress, and a lot of frustration. And that's exactly what we want to change with GoNeon. And we want to change this by providing the first AI agentic planning service that cuts design cycles from months to minutes and cuts entire infrastructure projects from years to months. But when we look at what AI can do today, we realized quickly that it's a very terrible city planner. It can create very nice images. It can write reports. It can analyze texts. But when we look at the results that it produces in the domain of city planning, we often realize that it fails to capture some relevant context that is necessary to make these results really reliable. And we see this exemplary in this picture with all the tram tracks that don't align and all the lanes that connect in a very weird way. So what are the inherent specifics of the planning discipline that make it so difficult to use pure AI? In principle, there are three things that make it so challenging. The first aspect is a very limited set of training data. When you think about it, when OpenAI uses images to train its model to generate other images, then it has billions and billions of images online of cats and houses and cars and people that it can use to train their diffusion models to generate these images. In the space of planning, we don't have this luxury. We have the plans that you can find online and that are produced by the engineering offices. They are much, much more sparse, and they are also much more fragmented. In different countries, we do things in different ways. We consider different requirements. So it's impossible to train diffusion models in the same way as we do it in other disciplines. The second challenge is that we pose very high reliability requirements. We won't tolerate if two one-way streets meet in a way that a vehicle cannot pass through, for example. So in the planning discipline, we need to create results that where things are actually correct. And the third thing is that we have very specific requirements. In every project, it's a bit different. We have local regulations that need to be considered, and this also makes it so difficult to use general models. So what we do at GoNeon in order to solve this challenge is we combine the creativity and the flexibility of large language models with conventional deterministic representation of the built environment. So you can imagine it like enhancing the chat, like in ChatGPT or in other large language models, enhancing the capabilities of the large language model with a very detailed and very reliable knowledge of how objects in the built environment are designed and how do they relate to each other. And when we have this representation of the built environment, then we can make conclusions and make changes to this representation where we can always ensure that, that the results are correct. There are three key elements of this representation of built environment that we use. The first element are networks. This could be, for example, a network of streets and intersections, where you have individual streets. Every street has a different width of the road space. Every street has different lanes, different vehicles that can use these lanes, and this can be represented in a network. And this network always knows whether it's connected, whether you can reach every building, whether you can, and how long does it take to reach destinations. The second part of this representation is a knowledge graph of other elements, like, for example, parking spaces or building entrances or individual utility infrastructures. And there, by representing these elements as ontologies and representing their logical relationships, we can again ensure that, that the built environment that we are working on and that we are producing stays consistent and complies with the rules. And that brings us to the third part of this representation, which is laws, regulations, and requirements. These can come in the form of unstructured texts, but in our engine, they are translated into a set of explicit structured instructions that can be then used to enforce consistency criteria on the knowledge graphs and on the networks. And as an example, what this enables is when we are for example, when we are looking at this individual parking space for disabled persons, by applying a set of rules from documents that have been provided by the city or by the engineering office that we work with, by applying this set of rules onto the elements in the knowledge graph, we can ensure that the design exactly complies with these rules, and every single property of this design can be traced back onto the specific rules that have been provided. So you have a design that is reliable, and you can always look back why individual aspects of this design are the way they are. Here is a simple example from one project where we looked into parking spaces. And we basically asked our design agent to check whether they comply with the applicable rules and regulations. And the design agent in the background performs the relevant checks and returns the answer. It tells you for every single parking spot, does it comply with the given rules or not? Another example could be testing a set of cycling routes in the city. That has been a big topic in Switzerland in the past years. Building such infrastructures across the city requires additional space, which is often acquired by removing parking spaces. but often it's very difficult to know in advance which parking spaces will have to be removed and how many and where. And this is something that in conventional planning processes, it may take months to perform these analysis, while using such an agentic planning approach, it's a question of just a few prompts and you get an answer of how could the parking situation change once you add these additional cycling infrastructures. One can also apply the same process on generating entire networks. So far we looked into individual elements like parking spaces, but you can also apply this whole process one level higher at the level of entire networks of streets and lanes. And what we see here is as a process of generating a set of lanes, set of lanes that are placed on individual streets according to certain design goals, like for example, adding greenery or adding cycling infrastructure, while ensuring that the whole network remains consistent. So when we reallocate this row space on the individual streets, the resulting network always remains consistent. So every intersection can be reached, the streets are connected, so vehicles can still travel along the entire network. One can apply this process either to create designs for individual streets or individual blocks, but it can be also scaled up at the level of entire cities. Like for example, here, this is the famous e-bike city project in Zurich that has been where an early version of this design process has been used to create the network-wide designs for an entire city. So you can explore a wide range of design options while looking at every single street, every single relevant detail, and ensuring that the results comply with the rules that have been provided. Obviously, these processes, they need a lot of data. You need to know how the streets are organized. You need to know what are the widths of the streets. So for this, we have also a set of ways how we can acquire this data, either from open source geodata, but also we can also use text-based data from like newspaper articles or from reports, or also image recognition. Also, it's worldwide also mentioning that the data can be provided in a modular way. So sometimes in some projects, it might not be necessary to have all the possible data, all the details of the data source of the data that one could think of. The first results could already be good enough, but if we notice in the process that something more is needed, then it's always possible to add additional data sources and see how the results will change and how important these additional data sources are. Now, how it works from a practical point of view, it is what we provide is a so-called agentic service, which has the advantage for the users that they don't have to install any new tool. They also don't have to learn any new tool. They basically provide their question and our agents work in the background and produce an answer. So it's a process where we take care of all the complexity on the technical side, and the user can focus on the question and on interpreting the results. There is also always a specialist from our team in the loop to ensure quality and ensure that the results make sense. Now, we currently focus on 3 different use cases. The one are mobility plans across entire cities. The other ones are corridor studies, like where do you route a new cycling route or a new bus route or a new bus lane. And the third use case are microscopic use cases like parking reforms, where we think about individual parking spaces and how do they relate to the public space. Our customers are typically cities, engineering offices, infrastructure operators, and development agencies. We usually leave the creative part of the planning process to the planning offices. They have a very good, strong relationships with the local stakeholders and with the cities, so they understand their needs, while we focus on the technical part of generating the scenarios and making sure that the planning process can progress very quickly. Now we are almost at the end. I want to also say great thanks to our team of dedicated entrepreneurs, planners, and developers, but also to our inspiring mentors and advisors. And it's really, really great fun to work with all of them. Now we are at the end. I want to point attention to our 100 Cities Planning Challenge. When you scan the QR code, you will get to our LinkedIn page where you can follow us and get newest updates about how this field is developing. And if you click on sign up, then you will come to our website where you can join a challenge. You submit a planning question. Our agents work for 1 week and provide an answer to your planning question. It's that simple. No need to learn any tools and no need to install anything new. Now we are at the end of my part. Thanks for attention, and I'm looking forward to a couple of brief questions.
Thank you. Thank you very much, Lucas, for the presentation. Sounds incredible, so that we can focus on strategy rather than on complexity. So I have one question already in the chat for you. So we will have 2 answered questions right now and then hand over to Lucas Ambühl. And then in the end, we will have another time to discuss other further questions. So one question from a practitioner is, how does AI operate with the needed flexibility around the regulation documents?
Mm-hmm. Mm-hmm. So clearly the regulations in planning, they often need a lot of interpretation. So if it says that something has to be 2 meters wide, sometimes it might also be less than that if it's justified. That's indeed a very good question. We also often identify contradictions in the regulations and the requirements, and by having this very reliable approach in the background, we can often identify contradictions that other people were not aware of. So that's also the part that requires the human in the loop at the end. That's where the planners basically have to say, okay, in this case, we alter the relevant regulation. In this case, we do it differently. In this case, we choose this one and not the other one. So that's exactly the role of the planner, to make these decisions.
And then another one would be, is the planning also underground or only overground?
Yes, so basically the planning can consider any constraints. So depending on how we build the underlying model, it can consider only the overground spaces, but if we include the underground infrastructure in the knowledge graph, then it can also consider the underground infrastructure as well. So it's up to the project.
And what would you say about the accuracy of the results you get from your AI tool in the end?
So it's very dependent on what the focus of the project is. Often, when we talk to customers, we have to early on agree on an appropriate level of detail and appropriate level of accuracy. And I think this is also something that in the planning discipline, we are often used to think about a lot of details, and it makes it difficult to then zoom out and think more about the concept. So sometimes having less accuracy and less details, especially at the beginning of the process, helps to open up the space and discuss more about the relevant relationships and the relevant trade-offs. And then we can increase the level of detail throughout the project. So to sum it up, the level of accuracy and the level of detail is very dependent on what is needed. So if we are working on individual parking spaces where it's about centimeters of road widths, then it's about centimeters. But if we are working at the level of entire street networks, we may want to think more about tens of centimeters or meters.
Thank you very much, Lucas. I see now questions coming in. That's really good for the end of the two presentation, but I will hand over to Lucas Ambül right now so that we can see the other one, and I will. So.
Perfect. Thank you very much. Thank you also for the presentation, Lucas. It's a pleasure to be here. Again, I'd like to give you, in the next few minutes, I'd like to give you a overview of what Transcality does, and also then deep dive a little bit into the AI applications that we have. Also, from a technical perspective, what we essentially are, we're a ETH spin-off. We were founded 3 years ago. I'm one of the co-founders, and we're by now 11 team members. We had the chance and the luck to work together with very large agencies, planning agencies, but also cities such as the city of Zurich being one of our best customers, obviously, but then also the canton, but also larger entities like Astra, which is the federal road office handling all the highway operations in Switzerland, or even larger transport for London or Barcelona. And what we build is essentially digital twins to rehearse the future of mobility, and we'd like to do this together. And in the few next minutes, I'd like to show you first kind of what the problem is that we are trying to address. And I think it's very common, as the other Lucas also talked about, right? Problems about increasing pressure on the current infrastructure, current transportation infrastructure, right? Increasing urbanization. These are all trends that I think you're all very familiar with, right? Net zero targets, how do we achieve them? And that together brings us to changing infrastructures and also changing mobility requests. And many of our clients usually come with a question as the one of the three that you see here, right? Can we move a lane for cars and add a lane for bicycles? And this is, a classical question that you might have after you have consulted GoNeon. You might come back and say, okay, but what are the effects on traffic, essentially, right? What is the impact on it? Or what we also hear very often is what happens if we close the main bridge for a month, or how can we alleviate the traffic congestion caused by this road closure? And this is why we built a digital twin. And before I explain exactly how the tool works, just this small animation which tells you a little bit what we mean by digital twin. We essentially take everything that moves around and we replicate how it moves around in a digital world, right? So we try to be able to answer afterwards questions like, what happens if you close the main bridge here? And not just at an intersection level, but really at the network level. And how this actually looks like, our solution, you'll see, is really a very simple to use application. It's a web tool, you'll see in just a second, so no need to install either, right? And also anyone should be able to use it. So it's this very simple to use approach. I'll come back to how we built this, what you will see in just a second, but let me just quickly show you the demo of it. So this is the demo for the city of Thun, which is a customer of ours. You can do 3 things. You can change the permission on a certain road. That was a bit quick. You can also change the speed limits or the turnings. And after a few minutes, you directly get the impact on what happens in your city. You get also a Google Map-ish type of speed map, or you get a view of how origin and destinations look like. You can also look into the regular KPIs that you're interested in, queue lengths or turnings, or you can look into spider maps that tell you from where vehicles come and go to. And in the background, there is a classical simulation, as you just saw it, that would double check, what happens if you close a certain road, as you just saw, with cars driving actually in a mechanistic model around. You can double check the effects compared to a base scenario, as you see here. Where do we see increases and decreases? And all of this in a web app, again, easy to use. And the word that is really important to us is that it's a collaborative approach, right? That anyone can access the model. Now, simulations have been out in the market for quite some while. There's nothing new about them, but I'd like to discuss quickly how we built them and how this is different from the current approaches. So at a very macro level, we have 3 steps. The first step being data ingestion, very similar to what Lucas told us before. We take different data sources, first and foremost being the openly available data sources for the maps, for the networks, to replicate the network into a digital replica. And then we go on and we add basically data from cities. That can be sensors, that can also be traffic signal data, but it can also be data about their public transportation system. And in a second step, what we do is we put everything together into this bucket, this second step here that you see, which is called AI and simulation, which I will be talking in just a second about a bit more. And in the last part, you'll have access to the platform, which you saw just before. Now, the special thing about this is that all of this is built in an automated pipeline way, right? So this is where the whole tech part comes in, is to make sure that we build such models instead of a few months or even years. We try to build them in a few weeks, and we're very successful at this, regardless of the size of the transportation network. Now, the webinar is about AI, and I wanted to bring up a little bit a classification, which I usually love to do, about different classes of AI. And I think Lucas has touched on a few already, and I'd like to put them into perspective a bit and explain how we understand the different AI classes there are and how they can be used in urban planning, and how we also use them as Transcality. The first class, which is a very well-established class, is the applied AI, which is mainly used for quantitative analytics, right? Here we're talking about finding outliers, anomaly detection, right? Or data imputation, which you'll see in just a second, and also short-term traffic prediction. The second kind of class would be generative AI, which I think Lucas has given a wonderful kind of overview already. It's more about qualitative analytics, where we're talking to a tool, where it's the natural interaction with the tool, where it's also good at text, at scenario summaries or reports. And the last part, which is, I would say, a newer hype or maybe a newer discussion going on, is the whole agentic AI, which is also still in an exploratory phase from our perspective, but also I think when seen applied worldwide. It really automates multi-step workflows. And what we see here is a promising future for AI orchestrators, as we would call them, connecting different models and application. And I'll give to each of them, I'll try to give an example. First, I'd like to deep dive a little bit into the first two ones, the applied AI and the generative AI, and how we explain them. Now, as you can see, again, I'm bringing back the same kind of tool chain as you have seen before, right? So we have data processing, we have a simulation, and we have first interpretation. And when we look into the first basically step, where it's all about data processing, here where we work with AI most of the time is about data imputation and anomaly detection, right? So you can imagine we have many different data types that come in. They need to be standardized in some way, etc. You'll see how we do this also in the very last step. But here you have a detector from Astra. So again, a highway detector that we had access to. This is in 2024. And this is in the morning from 6 to 9 o'clock. The detector just didn't send any data, which is a very classical thing. We flagged it as an anomaly, and we then impute the points how they could have been based on detectors that are next to it, or even detectors that are far away but that behave similarly, and also based on the history. So this is something that has been done for quite some years now and is quite the standard. The second thing that we do here is, I didn't mention this in the beginning, but we're also very much involved in building digital twins that can run in real time. That would mean that we always need to have some kind of prediction of the future of the next few hours. And what you see here is on the left-hand side, again, highway flows for a certain segment in Switzerland, close to the Gotthard Tunnel, which is an alpine tunnel, which always has a lot of congestion in summer times. And you see basically 4 stars representing the 15, 30, 45, and 60-minute prediction. And you see then the trace of this prediction, and you can compare it with the real measurement. And you can see that we're fairly close, and we can predict the speed drop very accurately in advance. It's clear that there's still some variances that we cannot capture, but we're doing quite a good job at the moment. And this is also something that we have deployed to all of the Swiss Federal Highway network, taking 3-minute values, and are using this right now. Now, in a second step, right, what we discussed is we're using simulation. And here, very similarly to what Lucas said, the model, the core model itself, remains deterministic, meaning that we do not allow AI to just predict whatever flows there are on certain roads, because we have found it to be super important that the results are still transparent and especially reproducible. And this for one main reason, because most of our customers would require us to be court proof, meaning that someone could look into, another expert could double check what are the assumptions behind what you did. And this is just done best, at least at the current state, with a simulation itself, with a deterministic kind of model. And here, as a side note, we use Sumo, which is an open source model. You can imagine that if you've been familiar with Vissim or Visum, kind of as the open source version of that part. But remember, we built the architecture around the simulator and not the simulator itself. And you can see here on the left-hand side the cars and buses and bicycles moving around for the city of Zurich. Green means that they're going at a speed of between 40 and 50 kilometers per hour. Red obviously means that they stopped at an intersection. And on the right-hand side, you can see the model of the city of Geneva, which is also a client of ours and uses our tool, where it's a little bit more red, but this is also because it's a different time of the day. Now, let me move on to the last point, which is this kind of interpretation, right, with generative AI. And here it's clear, and as Lucas also described it, right, we have similar ideas in terms of automatic extraction of the results and also processing and being able to discuss or interact with the tool in a natural language, and would then allow us to see some recommendation. What you see here is basically our first version of a data analyzer where you can upload many different types of data sets, which I'm sure you're familiar with in the traffic or transportation domain. There's plenty of measurements with different standards, different column names, etc. And this first step is kind of an analyzer that puts all these different data sets together into one box, where you can then actually have a preview of what goes on. But more importantly, it standardizes all the different kind of heterogeneous data sets. You can then also go on and ask questions, as in which detector has the lowest speed, for example, and it would then directly give you an answer. That's kind of a first step, right, towards these generative AI models, which then, as a first step, really bring together different data sets, standardize them. They can then be applied to the simulation, and in the end also recommend what could be done. I'd like to go on to one last point, right? Coming back to the different classes of AI, there's one step that one class that we haven't talked about, which I would still call exploratory, which is this agentic AI that people are talking about. And here, I'd like to quickly show you what we have been working on together with Rob, actually, where it's building an AI orchestrator. Now, what does that mean? I don't expect you to understand all the different modules shown here on this slide, but I think it shows kind of in a nice way how there is, let's say, a big boss called the orchestrator, which is an agent, right? So it's kind of you can imagine that as a ChatGPT, a certain person, digital person that is in charge of handling, data inflow, and then deciding which analyze module should be run on that data. And it then calls sub-agents, so for example, specialists that look into anomaly or look into clustering or look into other kind of functional relationships between the data sets. And then they all report back again to this main guy, the orchestrator, which is supported by, and this is fairly important in the literature also, a quality control agent, which reviews kind of what all these agents have produced in a critical way. So you see that these external agents then, here on this other side, can also interact, right? So it's kind of, for example, a simulator could be run by an agent calling basically our Sumo, as you saw before, right? And would then result in some KPIs, etc., which then could then be reinterpreted by the orchestrator and reviewed by the quality control. Now, GoNeon fits here perfectly because it's as you can see, a planning tool, and it essentially has its own army of agents. And so you can see that basically in the end, what these agents try to do is facilitate the interfaces between different tools. That's their idea. It's really not replacing everything that we do as a human, but it facilitates really these interactions between different tools, which in very many cases we're in these silos and don't get to the other part of the silo or of other silos. Now, with that, I would like to come almost to an end. And obviously, from a research perspective, limitations are always important. Lucas has already touched upon some of them. From our perspective, right, AI depends heavily on data. I wanted to say heavenly on data quality. Maybe it's also heavenly, but it also heavily depends on data quality and availability, right? So garbage in, garbage out. This is why we believe, just as GoNeon as well, deterministic models remain essential for transparency. And a next limitation for generative or predictive AI is that Gen AI learns from the past, right? So that means that in order to create new ideas which have not been tested or actually described by anyone in the past, it is fairly hard for Gen AI to come up with that. So that always requires, therefore, this human in the loop, not just to avoid hallucinations. And last but not least, explainability in our field remains a key, right? Because we work for the public sector. They are accountable, and also, therefore, our decision-making processes need to be human-led in the end, so that there is an accountability throughout the process. Nonetheless, right, we believe that that AI, in all the forms that I showed, are very, very powerful for heterogeneous data sets, predictions, and also first, I put that in parentheses, right, because we said the human needs to be in the loop, recommendation for urban planning and traffic impact studies. And with that, I'm happy to show you the last slide, which is the same as the first one, bringing back the core idea that we have, which is rehearsing the future of mobility together. And I would be happy to see you sign up also on LinkedIn, also on our LinkedIn, and maybe even talk about what we discussed right now together in the future, also offline. Thank you very much.
Thank you very much, Lucas, for your impressive presentation. And I'm impressed about that you can come up with solution as well. So that was one of my questions, but you solved that already. And we have some question within the chat, but also I see it's also possible to put your hand up, and I can allow to speak your question by yourself. So Laura has a question as well. So I would suggest we go first, try Laura, and then we go to the chat questions as well. So please, Laura, I allowed you to speak. We will
Hi,
try.
Laura.
It doesn't work. So I come up with the first question from the chat. So when we trading off different competition, or no, is it possible to develop scenarios or concept that drive a mobility system aligned with climate neutral objectives?
Yes, good question. So I think it's definitely possible. The question is, what kind of solutions that you have in mind. So I think at this stage, we still need to kind of feed in these ideas, at least at the current stage of our development. It's not that you can just click on a button and then it will tell you exactly how it should look like. I think these matters are fairly complex, right? And I think what you could do, right, in the first step is to evaluate certain ideas with Lucas's Palos tool, right, where you actually look into different variants very quickly and then pick one variant and test it within the traffic impact study, right? What would then happen to congestion, etc.
Thank you. And do you cooperate with university living labs and evaluating designs is one other question.
I mean, I think both of us have a very academic background, so I think we're very open and understandable to or understanding towards universities and are more than happy to collaborate, right? And as a matter of fact, we have multiple master theses going on at the same time, so we do this many times.
Same for us. We also have master thesis supervised, and also back to the question before. One of the biggest strengths of these approaches that both of our teams develop is that you can test a wide range of variants very quickly. So you can think about, so you can not only design the infrastructure according to one single principle and then have to focus on that one, but you can instead explore a wide range of options and then explore also the trade-offs that you have. So yes, designing transportation systems according to sustainability criteria, that's one of the most important goals.
Good, thank you. And then another one is, what is the difference to a classic GIS work and or the Gesamtverkehrsmodell we know in Switzerland? So if you have a holistic approach of a whole city with modeling.
I think it's pretty much the same for both for both technologies. It enables you to be much faster, and it enables you to focus on the actual creative part while the technology in the background takes care of all the technical details. So when you think about GIS, yes, you could theoretically solve many of these issues in GIS, but it would just require months and months of technical work, and you would need to think about all the details, how they are implemented, while relying on these AI-based workflows enables you to be much more effective and try out things without being overwhelmed by the technical details. And I think in case of Transcality, it's exactly the same for simulation.
Yep.
Okay, thank you. We try again with Laura. She's now within our webinar, so maybe she can open her mic. Otherwise, another question, will the tool be for future development for other planning issues, not just mobility, but also maybe housing developments, whatever, on possible to use that as well in the future?
So in our case, it is really quite universal what kind of issues you can address with it. We, however, deliberately decided to focus on mobility right now because A, it's the space that we know the best, where we know the needs of the customers the best and we know the customers the best, and B, where we clearly see some of the greatest challenges happening. But of course, in the future, we are open to other challenges as well. And in case of transcality, it's very similar.
Agreed. Most of the focus right now is on traffic transportation. Yes.
Okay. And then there is another question about if we can provide them your slides, and we try to figure out how it will be possible in the future afterwards. And then another question to Lucas Ballo: when trading of different competing design variants of how to allocate road space, for example, in certain road, you should place parking spots or make more space for cycling path. How does your model decide which variant are better?
We typically try to produce a number of variants, so it's not just one solution, it's usually a choice. And then there is a number of criteria in the background that is being used to prioritize. However, just like with AI, there is a lot of flexibility. So I'm sure most of you know this experience from writing with ChatGPT. You can steer a lot of its behavior by prompt engineering and then by asking it to do certain things. So even this prioritization of the different variants, you can control a lot by asking the right questions.
Good, thank you very much. Yeah, and there is another one, maybe one of the last. What LLMs do you use in the background? Maybe a question for both of you.
Yeah, so this is a good question. So obviously we are we do benchmarks with the big ones to double check which has the most powerful. We are, let's put it this way, without giving too much away, we are fans of open source models because it allows us to double check what goes on, etc. So I would put that into the front of this answer.
Mm-hmm. In our case, we work with a wide range of models, and there are some models are better in certain with more structured data. Some models are better with more general data. But in overall, it actually doesn't matter that much because the core of the challenge is not about the LLM itself, but it's about what tools do you use to equip, tools do you equip it with? So how does the logical representation of the built environment works? That's where the big challenge is. And how do you orchestrate the different AI agents together?
Cool, thank you. And then there is another one. Is it also possible to obtain a cost estimation for the different mobility scenarios? Maybe that's for Lucas.
Yeah. Clearly, you can provide information about how much do the individual elements cost, and then in the background, it will calculate a cost estimate for you. Again, it very strongly depends on the data that you provide. So when it's the goal of a project to also provide cost estimates, then we also feed in some standard values for how much do the different elements cost. And within the knowledge graph and within the representation of the built environment, it can be then calculated what are the effects of these different variants.
And do you already have experience with public participation where the solution accept and tolerate it? And how could the tool be used in this regard?
So from our side, right? So the participation process with the public itself, we have not done with the tool yet. However, what we have done is that it has always been a multi-stakeholder process, right? With engineering offices, but also the city, and within the city having multiple departments, right? So just to give you an example, for the city of Zurich, usually it's the public transport office, but it's also the Tiefbauamt, meaning the Department of Construction, and then also the Department of Traffic that are sitting at the same table, and then actually looking at basically a combined view, which everyone understands and everyone understands the same language behind it, has been very powerful, right? This kind of easy to access, easy to interact with. I think this is really the let's say in a way the game changer, right? Which allows non-technical or let's say non-experts, right? To also access these type of questions, which I think, Lucas, you put it very nicely, right? Because the solution in the end, which is then implemented, is really in the foreground, and not whether the distance between two cars is 1.35 or 1.36 meters.
Yeah, exactly. And exactly with this in mind, we just completed a project which was about public participation. It was in a part of London where they were conducting a discussion about future allocation of road space and how much capacity on the streets they have to be, and where do they place the priorities. And our approach was then used to actually create the scenarios and design them as we speak. So that's a major, I think that's a major game changer of these approaches, that you can actually conduct public participation where you can test the different scenarios during the deliberation. You don't have to take all these ideas with you and then take another 2-3 months to design everything, and perhaps you don't have any budget for that anymore. So at the end, it will not be done anyway. But with these approaches, you can actually, whatever proposals people bring, you can just test them and see what consequences would it have, and then continue the discussion from there.
Good, thank you very much. We have just one and the last brief question. Have you worked in the development cooperation sector yet?
Lucas?
So it has always been on the table. We have one more feature that is rolling out very soon, which will enable basically to create new, let's say, zones in our model, which then would allow to generate new traffic. So you could look into that. So it's definitely on our roadmap for the next month, but we haven't had the chance yet. So if you are, please reach out, and we're happy to.
Yes. Yeah, it's very similar for us. We are talking right now to multiple potential clients in that space. We are also, it's something that we are also now developing as an extension of the technology to be able to add new streets and add new plots and subdivide the plots. So it is definitely something. It's definitely an important area. We feel, especially from customers from emerging markets where cities are actually growing and all new areas are being built up. So it's a very important market, and we are looking into that.
Thank you very much, both of you. It was a pleasure to host you and see what you're doing. And I'm really looking forward also, because we are planning for next year a webinar series, which will have different topics on city planning and urban planning. So I will show that and make it public on LinkedIn or on our website as well. So thank you very much, and hope to see you soon.
Thanks for being with us, and thanks for organizing.
Thank you very much.
Thank you very much. And just one thing, we will publish the record on YouTube as well, so you can see the records as well in the future. Thank you.
Thank you.
Bye-bye. Cheers.